All right, so this is section 4.3, Complex Zeros, Fundamental Theorem of Algebra. So we are going to talk more about zeros. So a complex polynomial function, so a variable in the complex number system is referred to as a complex variable. A complex polynomial function f of degree n is a function of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1, etc. So we get a1 x plus a0, where a1, an minus 1, a, and a0 are complex numbers. As before, a is called the leading coefficient. A complex number r is called the complex zero. Okay, so let's see what, that brings us to the fundamental theorem of algebra. Every complex polynomial f of x of degree n greater than 1 has at least one complex zero. So if your degree is greater than or equal to 1, you have at least one complex zero. Every complex polynomial function, f of x, of degree n greater than or equal to 1 can be factored into n linear factors, not necessarily distinct, of the form a sub n times x minus r1, where r is the real, is the 0, times x minus r2, all the way until we get to all the x minus r, all the roots or zeros listed, where an, r1, r2, and rn are complex numbers. That is, every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. So let's apply this. We're going to let f of x be a polynomial whose coefficients are real numbers. If r equals a plus bi is 0 of f, the complex conjugate r is equal to a minus bi. So we change the sign in between our constant and complex components. Is also a 0 of f. The corollary is a polynomial f of odd degree with real coefficients has at least one real 0. So if you were an odd degree and you have real coefficients, then you have at least one real 0. There's at least one place you cross the x-axis. Tons of stuff. So let's look how that applies. A polynomial of degree 5, whose coefficients are real numbers, has zeros -2, -3i, and 2 plus 4i. Find the remaining two zeros, because same amount of zeros as the degree. So our first 0 is going to be -2, so we write that. But we look at our complex numbers and we write the conjugates of our complex. So since f has coefficients that are real numbers, complex zeros appear as conjugate pairs. So it follows that 3i and the conjugate -3i are zeros. 2 minus 4i and 2 plus 4i are zeros. So you just look at the complex ones and take the change the sign of the part with the I. All right, we're going to find a polynomial function with specified zeros. This is exciting. So we have a degree 4. The coefficients are the coefficients are real, and the zeros are 1, 1, and 4 plus I. So let's put that into, we need to find our other 0. So since 4 plus I is a 0, 4 minus I is also a 0. So let's write that as roots, or so we don't know our leading coefficient a, but we definitely know that x minus 1 times x minus 1, that takes care of these two zeros. And then you've got x minus the quantity 4 plus I, and then x minus the quantity 4 minus I. And then we gotta multiply this all out. You guys are gonna love this. Multiply this all out. So this guy right here becomes x squared minus 2x plus 1. And then this guy becomes x squared minus 4 plus ix. Boop. And then x. So 4 minus I times x, and then 4 plus I times 4 minus I. So we're going to simplify this down a little bit. And we get negative 4. So we distribute the x into the parentheses and then apply the negative. So we get negative 4x, negative ix, negative 4x, negative and negative make positive ix, and then 4 times 4 is 16. 4 times negative I is negative 4i. I times 4 is 4i, and I times negative I is minus I squared. Okay, so let's simplify this down. Thankfully, x squared stays. Negative 4x minus 4 more x's becomes negative 8x. Negative ix plus ix cancel. 4i minus 4i cancels. And negative I squared becomes, I squared is minus 1, minus a negative 1 is positive 1, and 16 plus 1 is 17. Woo! When we FOIL that out again and combine our like terms, we get a times x to the fourth minus 10x cubed plus 34x squared minus 42x plus 17. All right, so go ahead and when you're at home, do this on your graphing calculator. Graph the function f from our example 2, and let's let a equal 1. Does the value of a affect the zeros of f? How does the value of a affect the graph of f? What information about f is sufficient to uniquely determine a? A quick analysis of the polynomial function f tells us what to expect. For large values of x, the graph will behave like y equals x to the fourth. A repeated real zero at 1 of even multiplicity. So the graph will touch the x-axis at once. It touches it, but doesn't cross. The only x-intercept is at 1. The y-intercept is at 17. Figure 51 shows the complete graph. The graph has exactly 3 turning points. So we have 1, 2, 3. The value of a causes a stretch or compress. A reflection occurs if a is less than 0. The zeros are not affected. If I multiply 0 times anything, I'm still going to get 0. So if any point other than an x-intercept on the graph of f is known, then a can be determined. For example, if 2, 3 is on the graph, then f of 2 equals 3. And a, which is also equal to a times 37. So a has to be 3 over 37. Okay, so let's go ahead and find the complex zeros of a polynomial function. So here we have the 0. We want to find the complex zeros and write it in factored form. So the first thing we have to realize is that the degree is 4, so there will be 4 complex zeros. The potential rational zeros are the factors of negative 20 divided by the factors of 1. So essentially it's all the factors of 20. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. So we start testing. So we're going to test 2. I would test the 1s first, but I think for time's sake. They are testing 2. So we try out 2. Pull down the 1. 1 times 2 is 2. 2 plus 2 is 4. 2 times 2 is 8. 1 plus 8 is 9. 2 times 9 is 18. Negative 8 plus 18 is 10. 2 times 10 is 20. Negative 20 plus 20 is 0. So I know that 2 is a root, so I can write it as x minus 2. And then starting with x to the third, because we've already factored one of our x guys out of there, we got x to the third plus 4x squared plus 9x plus 10. Okay, so we're going to start that again with our cubed. We're going to test our what factors of 10 are possible solutions divided by 1. So let's try negative 2. 1 comes down. Negative 2 times 1 is negative 2. 4 plus negative 2 is 2. Negative 2 times 2 is negative 4. 9 minus 4 is 5. Negative 2 times 5 is negative 10. 10 minus 10 is 0. So my new guy is x plus 2. So I got x minus 2, x plus 2, and then x squared plus 2x plus 5. So now I should be able to factor this guy. And if he's not factorable, then we have to use the quadratic formula to find the zeros. So we set this whole thing equal to 0. And you get x minus 2 equals 0, x plus 2 equals 0, or x squared plus 2x plus 5 equals 0. And unfortunately, we have to use the quadratic formula. This one is easy. X equals 2, x equals negative 2, and this guy using quadratic formula. There's no two numbers that multiply to give you 5 and add to give you 2. So we're quadratic formulating it. Negative b plus or minus b squared minus 4 times a times c. So that is (4 minus 20). That's negative 16. The negative square root of 1 becomes the I, and the square root of 16 is 4. And then I divide negative 2 by 2, and I get negative 1. And plus or minus 4i divided by 2 is 2i. So I have a solution negative 1 plus 2i and negative 1 minus 2i. So let's put that all together. So the complex roots are negative 2, 2, negative 1 plus 2i, and negative 1 minus 2i. I know these look like real numbers, but real numbers can be complex as well, because it's like negative 2 plus 0i. So it says 4 complex zeros, and these are real number solutions, so they get to be zeros as well. All right, so if you write that as a polynomial, you get your x minus 2, your x plus 2, x minus negative 1 plus 2i, and x minus negative 1 minus 2i. And that's all she wrote. Thank you guys for joining me.